Okay, so we need to talk about something called covalent bonds and covalent compounds today. Last chapter we dealt with ionic bonds and ionic compounds, right? And we said that ionic compounds, the way that a compound such as NaCl, the way that it's held together is it's held together by the opposite charges of the two ions that are formed. So basically, Na is in which column in your periodic table?
1A.
Column 1A. So Na has how many valence electrons? 1, because it's in column 1A. Cl is in which column? Column 7A, so it has seven valence electrons. So Na wants to get rid of its one electron to become ideal, and Cl wants to gain an electron to become ideal. And so these Na and Cl become Na plus and Cl minus, right? This becomes positively charged, this becomes negatively charged. And so it's those charges, those opposite charges, that hold that compound together, right? That's what we call an ionic bond between these ions here, and the compound we refer to as an ionic compound. Well, there's a different type of bond that we have in these compounds that are formed, and this new type of bond is called a covalent bond. And with covalent bonds, rather than giving and taking electrons like what happened here, and then the opposite charges holding it together, covalent bonds, the atoms actually share electrons to hold the compound together. So a covalent bond, by definition, is a chemical bond made by sharing electrons. They don't give and take electrons the way ionic compounds work. They actually share the electrons in a covalent bond. So let's consider for a moment chlorine gas. Chlorine gas has this, that's how you would write down chlorine gas. It's two chlorine atoms that are bound together, and they're bound together with a covalent bond. Let's think about the Lewis structure of a chlorine atom for a moment. So I'm going to draw it like that. What do the dots around the Cl represent? The valence electrons. It has 7 valence electrons, so I put 7 dots around it. Normally, I told you guys, normally you would, if I just asked you for the Lewis structure of a chlorine atom, you would start at the top and you would start adding dots until you got 7. So they wouldn't be set up quite like this, but for the sake of showing how this bond works, I'm going to draw it this way. So I'm going to draw one chlorine atom like that, and then I'm going to draw another chlorine atom like this. They both have 7 electrons around them, right?
Sorry to interrupt. I need to speak to Caden real quick.
Okay, yep. Go ahead. So they're sharing these so these electrons here, this guy needs 1 electron to be ideal, right? This guy needs 1 electron to be ideal. So what happens is that this guy shares that electron, right? And this guy shares that electron. So they each share. So for a time, what happens is that as the electrons are being shared back and forth, for a time, one chlorine atom will be ideal, and then for another time, the other chlorine atom will be ideal, right? And so the way that we would write this down is we would actually write them together, right beside each other, and we would just show that these two electrons here are shared between the two. All right? And rather than write the dots, just so that we're clear that those electrons are being shared, we would instead replace the shared electrons with a single line. Okay? So we would draw it like this. So if you see the single line between it, the single line represents a single pair of shared electrons. So if I said write the Lewis structure for Cl2, that's how you would draw that. You good?
Yeah.
Okay. And so you see how the sharing works. Like for this Cl here, if I draw a dotted line around it, for some of the time, because they're sharing these 2 electrons, for some of the time that one will have 8 electrons, and for some of the time this one's going to have 8 electrons. So through the sharing process, they can kind of attain that ideal state some of the time because they're sharing those electrons. I say some of the time because remember these things are like orbiting around. They're not just staying still, right? The electrons aren't staying still. So they're orbiting around and passing between the 2 atoms. But that's how a covalent bond works. They share those valence electrons so that they will be in an ideal state. Any question about that? Questions about that? So whereas ionic bonds are these opposing charges that hold it together, covalent bonds are physical bonds because they're physically sharing the electrons. That's what holds them together. And we draw a dot for the shared ones. I'm sorry, a line for the shared ones. We continue to put the dots for the electrons that aren't shared. This bond is actually stronger than an ionic bond because it's a physical bond versus just one held together by the charges of the ions. So Cl, this molecule right here, Cl2, we call this a homonuclear diatomic. And a homonuclear diatomic is a molecule consisting of 2 atoms of the same element. So 2 chlorine atoms bound together with this covalent bond. All right? And the reason I'm highlighting this is because there are 7 elements that naturally that's the way that they occur. Like if you've got a bunch of chlorine atoms floating around, they're not going to stay as single chlorine atoms. They're going to bond together as Cl2. All right? So there are 7 elements that exist like this, and you need to memorize these. So I want you to memorize the homonuclear diatomics. They are H2, N2, O2, F2, Cl2, Br2, and then I2. And since you get to use your periodic table on the tests, right, one of the ways that you can remember these 4 here is they're the top 4 elements in column 7A in your periodic table. So, top 4, column 7A.
So you only want us to memorize those 4?
I want you to memorize all 7,
Okay.
but since you'll have access to your periodic table, that'll help you identify at least 4 of them, right? If you remember the top 4 in column 7A, and then if you can just remember H2, N2, and O2, you'll be good. And the reason why you need to remember those is because when we start doing chemical equations, if I were to say, write down the chemical equation for the formation, for example, of water, this is not the chemical equation for water because hydrogen and oxygen are both homonuclear diatomics. So they're going to be floating around like that as H2 and O2. All right? And then so you'd have to write it like this on this side of the equation to get credit for that. And then you'll also learn how to balance it. Like technically it would be, that would be the balanced version of that, what we call the formation equation, the forming of water, right? But you've got to know that H2 and O2 are homonuclear diatomics in order to get that problem right. So I need you to memorize these, okay? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and then iodine are all homonuclear diatomics. Questions about what a homonuclear diatomic is? Is everybody clear? So as far as what's floating around out there, you don't have, when you have hydrogen floating around, you don't have a single hydrogen atom. You actually have a hydrogen molecule, because a molecule is comprised of more than one atom. And so you've got two hydrogen atoms that are covalently bound together. And so you have a hydrogen molecule. Okay, so let's see. Let's talk about the Lewis structures of covalent compounds. I figured I was going to run out of room. Lewis structures of covalent compounds. Let's do some of those. Let's see. All right, let's start. Let's start with carbon. So we got a carbon atom. What's the Lewis structure for a carbon atom? How many dots around it? 4. Because we can call them 4A. Who said 4? Elizabeth? Four dots around carbon. How many dots does hydrogen have? 1. I heard multiple, so I don't know who to give credit to on that. You'll have to impress me again later. So let's say we've got 4 hydrogen atoms, each with 1 valence electron. Carbon wants to have how many?
8.
8. It wants to have 8 to be ideal, right? This is getting confusing with the marker. Lily. I'm going to take a picture of that and I'm going to go home and I'm going to go, why did I do Elizabeth's name in black? I don't know. She had a black jacket on.
She's the Maui girl.
She is the mouse, right. She's different from all the rest, right? All right. So, so carbon has 4 valence electrons, but it wants to have 8. What about hydrogen? How many electrons does it want to have in order to be ideal?
None.
2. You're right.
Why 2?
Why 2? Because hydrogen, you were thinking none because usually what we see in that first column there, those are metals generally, and they're getting rid of their electrons, right? But we're not talking about ionic compounds now, which are comprised of metals and nonmetals. We're talking about covalent compounds, and it turns out hydrogen is actually a nonmetal versus a metal. So it's trying to gain electrons the way all the other nonmetals do, right? To gain electrons to become ideal. Why does it only need 2 to be ideal?
Because it only has 2.
Because it's a homonuclear.
There's some good guesses. How do we know what an ideal state is if we look at the periodic table? We know what the ideal on each of these rows here.
In the s orbital,
right?
It only needs 2
2, right? In the s orbital, it only needs 2. And so helium, if we looked at the inert gases or the noble gases on the far right of our periodic table, those always have their outer energy level full, right? And so for neon, that means it has 8 electrons in its outer orbitals. Remember, it has an s and a p orbital. Both of those are full. One has 2, one has 6 in it. And you go on down, that's the case for all of these: neon, argon, krypton, xenon, all of these except for helium, which is at the top. Helium only has the s orbital, like you were saying, right? It's totally full. It's a noble gas. But since it only has an s orbital, then it only has 2 electrons there to put it in its ideal state. Well, anything that's to the left of the periodic on the periodic table that's a non-metal, it wants to be like the noble gas to the right of it. Okay, so everything except for hydrogen is going to want to have 8 because the noble gas that's to the right of it has 8 electrons. But for hydrogen, the noble gas to the right of it is helium, which has 2 electrons because it's only got the 1s orbital. So hydrogen only needs 2 electrons to be ideal. Okay, so you got to remember that about hydrogen. Hydrogen only needs 2 E's to be ideal. All right. So carbon needs 4 electrons to be ideal. Guess how many total electrons we have with these 4 hydrogen atoms? We have 4 electrons hanging out there, right? We've got 4 hydrogen atoms here that each want 1 more electron to be ideal. So we need a total of 4 to match up with this. And guess how many electrons carbon has to offer? 4, right? So what happens is that these guys will, how am I going to draw this without being too confusing? These guys are going to share an electron pair here. They're going to share an electron pair here. I'm going to put those dots on the bottom here so I can share them a little easier. These are going to share electron pairs here, and these are going to share an electron pair, right? So now, by sharing the electron, all of these atoms are ideal. So let's draw what the final Lewis structure looks like. So between each of them, there's going to be a shared pair of electrons. So we'll draw a straight line to signify that. And there's no electrons that aren't shared, so we don't have any dots in our final Lewis structure. It's just a C in the middle with all of these lines representing covalent bonds or shared pair of electrons. And so if you think about this from the standpoint of, I'm going to draw carbon again as black in the middle here. If you remember that a line represents a shared pair of electrons, so when you're counting electrons, always count a line as 2, right? One line is 2. And so if we think about that, if we put a dotted line around all of the lines that are around carbon, 2, 4, 6, 8, so carbon is ideal. If I put a dotted line around the H to count the electrons here, this H has 1 dotted line next to it, so it's got 2, which is all it needs to be ideal, right? So everybody's happy. Everybody's got the ideal amount of electrons because of the covalent bonds there. Questions about that? Anything confusing in that process?
Can you explain why hydrogen only needs 2 electrons?
Okay, so really the best explanation is the fact that that is the electron configuration for hydrogen. Remember when we were writing our electron configurations? It's that. And what's the max number of electrons S can hold? 2. So if it has 2, then it is full, right? Hydrogen's the only one that only has a single S orbital, right? From there you jump up to the next energy level starts the P orbital. Yes?
So, and you also said because it wants to be like helium.
That's right.
Helium has to. So who does helium want to be like?
Nobody, because it's a noble gas. It's already ideal. All of those in that far right column are already ideal. Okay. They're noble or inert because they don't typically react with any other elements because they're already happy, right? They've already got their ideal electron configuration. Do you have another question?
No.
No? Does someone have their hand up over here? All right, no?
No.
What was it? Were you channeling a question to me?
No.
Little Maui experience going on? No? Okay, all right. All right, is that clear though? Yes, okay. All right, so let's see. So we talked about covalent bonds. We talked about the Lewis structure of covalent compounds. You have to remember hydrogen is the one element that only needs 2 in these reactions in order to be ideal. So this is a obvious definition, but I'm going to write it down anyway because he had it in the book, and of course you need to know this. But a covalent compound is a compound this should go without saying, but you know, a compound whose elements are held together with covalent bonds. So if it's an ionic compound, ionic bonds hold the compound together. If it's a covalent compound, covalent bonds hold the compound together. If it's ionic, opposite charges hold it together. If it's covalent, the sharing of electrons is what holds it together. It's a physical bond. You can look for these by looking for metals. If I just wrote CH4 on the board or on a test and I said, is that an ionic or a covalent compound? You would simply go to your periodic table and you would look at the color of C and the color of H on your periodic table. Both of those are blue, which means they're what?
Non-metals.
They're nonmetals, so they don't have any, there are no metals in this compound. And if there are no metals in the compound, then the compound is covalent. All right? So a compound whose elements are held together with covalent bonds will not contain metals. Only nonmetals, and sometimes metalloids. And if you look at your periodic table, you'll see there are a handful of elements that are identified as metalloids, which are kind of start with boron and call them 3A and kind of go diagonally down to the right. So 6 elements there identified as metalloids. Covalent compounds will always be composed of those. So you're primarily looking for if you see a metal, it's ionic. If you see no metals, then it's covalent. Okay? Everybody got that simple rule so you can identify the two on a test? All right. Let's do an example. Example 5.1 on page 130. And it says, what is the Lewis structure of NCl3? Let's draw the Lewis structure for NCl3.
What page?
130, I think. NCl3. What's the Lewis structure for NCl3? So we know we've got 1 nitrogen atom and we've got 3 Cl atoms, right? Nitrogen is in which column? 5A, so it has how many valence electrons? 5, right? So I'm going to draw those, let's see. I'm going to draw those like this. Cl is in column 7A, right? So it's got 7 valence electrons. I'm going to rearrange them in such a way on my Lewis structure here so it'll be clearer to identify where the electron pairs are. Okay? So it's kind of like a puzzle, right? If you sort of think about rotating these guys in your mind, if I were to take this Cl, well, first of all, usually when you're drawing these Lewis structures, there's going to be a central atom. There's going to be an atom that's kind of in the middle of your Lewis structure. And usually that's going to be the atom that needs the most electrons to be ideal. Okay? So each of these guys only need 1 electron to be ideal. This guy needs 3. So we're going to think about him being in the center, all right? And the Cl, all the other Cl atoms hanging off of him, right? So if you kind of think about this as a puzzle in your mind, and you kind of think about Cl, taking the Cl and rotating it and plugging it in there, then this electron will be shared with that one. This guy here, we'll take it and we'll rotate it and plug it in there so that this one and this one are shared together. And then we'll take this guy and we'll rotate it up underneath here so that those two are shared together. So the sharing is going to be these two these two, and these two, right? And so we've got 3 pairs of shared electrons, so we're going to draw, like I said, the N in the middle. We know we've got a shared pair between one Cl, a shared pair between another Cl, and a shared pair between another Cl. So we've got that portion of the Lewis structure written. The only other thing we have to do is we've got to put dots for all of the electrons that are not shared. Okay? So for N, there are 2 remaining dots that aren't shared. For each of the Cl's, there's going to be 6 remaining dots that aren't shared. We'll add those on there. So it looks like that. It doesn't matter if you had put the Cl, this Cl here on top, or if you've taken this Cl and moved it to the top. I don't care, right? It doesn't matter where they are in relation to one another, as long as you identify that there's a shared pair of electrons between each of the Cl atoms and the nitrogen atom, and then you put the remaining dots there. So the best thing that you can do when you get done drawing your Lewis structure and you think you've got it accurate, count your electrons. Right? Make sure that each of them, except for hydrogen, for hydrogen you're looking for 2, but for everything else you're looking for 8 electrons around it, right? So if we count this, we've got 6 electrons here. Each line represents 2 electrons, so we've got a total of 8 there. So if I count everywhere, here we've got 2, 4, 6, 8. We've got 8 around the end. So make sure that you have a total of 8 electrons around everything. 2 if hydrogen's in the mix. Any questions about that? Pretty clear on how we did that? And then they asked us to do H2O also. So let's do H2O. Hydrogen, 2 of those with a single electron. I'm going to go ahead and write my O in the middle. So we're going to do my O like this. O has 6 valence electrons. Hydrogen has 1 valence electron. Hydrogen wants 2. Oxygen wants a total of 8. So what happens? These guys share here, and this guy shares here. And so the final Lewis structure looks like single bond between the O and the H's. And then we've got to account for the non-shared electrons, so we're going to put dots there. Notice in the book, again, the orientation of this doesn't matter. They did it like this, where they had an O like that. That's either way is fine with me, where you put those. It's going to matter in the future, but for now I don't care. I just want to make sure that you understand where the covalent bonds are and the number of electrons that are not shared. Okay? Any questions before we move on? We have a break next week, no class, and this kind of stuff's going to be on the quiz, so I just want to make sure that you understand it, since it's going to be 2 weeks from today when you have your next quiz. I want to make sure you're clear. All right, if no questions, I'm going to move along to, let's see, what's next? More complicated Lewis structures. More complicated Lewis structures. So, we've already done the Lewis structure for Cl2. All right, let's do the Lewis structure for another homonuclear diatomic. Let's choose O2. O, how many valence electrons? I think I heard Jerry first. 6 valence electrons. Just like this. We draw another O. We're going to give it 6 valence electrons as well. I drew it that way so that we can see if each of these guys need 8, this oxygen can share this electron while the other one shares that one. They become an electron shared pair. And then they can share those two and become an electron shared pair. And so oxygen, as it appears naturally as a homonuclear diatomic, the oxygen molecule is actually an example of a double covalent bond. So a double covalent bond, again, each line, as long as you remember each line always represents two shared electrons, just count it as two, right? So when you're counting up to make sure that you've got the right number of dots and the right number of lines, we've got 1, 2, so 2 here, 4, you count those two, each of these count as 2, 6, and 8, right? So we've got 8 around this one, and we've got 8 around this one. So 8 electrons around each oxygen. They drew it like this in the book, but there's this cool Star Wars TIE fighter that resembles more. You know, it's like a double pod TIE fighter. So I like this version better. Somebody said in Cloud City there were some like things that flew that looked like that as well. That's what I always think of when I draw that. All right. Questions about double covalent bonds, right? So we've got single bonds represented by one line, double bonds represented by two lines, and guess what?
Oh, I thought that was an equal sign.
Yeah.
That makes sense.
Triple lines that represent triple bonds. So there's another homonuclear diatomic that we could draw its Lewis structure to see one of those, and that would be nitrogen. So nitrogen is in column 5A. So nitrogen has 5 valence electrons. Probably should have done that. Let's see, I'm going to orient them like this. I'm going to do 2 over here, 2 right here. Yeah, that's the way to do it. So that way these guys are shared, these guys are shared, and these guys are shared. I kind of want to make, this is like one of those things, you know, the psychiatrist says, tell me what you see.
Real loud.
It's like there's something in there. I can't quite figure it out, but it's speaking to me. So anyway, this is we've got 3 pairs of shared electrons, and then we've got 2 that are unshared for each atom. So that would be the Lewis structure for the nitrogen molecule. Any questions about single, double, triple bonds? By the way, this is the weakest, and this is the strongest. So the more covalent bonds between atoms, the stronger the bond is, the harder it is to break. Yes?
Can there be like a quadruple bond or anything higher?
We don't cover that in here. I mean, you could see where like something with carbon, right? Carbon has 4 and it needs 4. So if you had a carbon atom, why couldn't you have a quadruple bond? But we don't cover it in here. So that makes me think that it's probably not very common. Or maybe not naturally occurring. I'll have to look that up. I'm not sure. Yes, you have a question?
Nitrogen, the covalent bond, like the thing with the 3 lines,
Uh-huh.
is it supposed to have 2 more electrons on each side?
Nope, and the reason we know that is we count them up, right? So we've got 2 here. Each line represents 2 electrons. So 2, 4, 6, 8.
Okay.
Right? So you have a total of 8 around each one. Make sense?
Yes.
Yeah, always count your electrons at the end just to make sure you haven't done something wrong, right? If you'll do that at the end, that'll keep you from, making some kind of silly mistake. Make sure you get full credit for it. So I need to do an example, but I got to tell you guys, every time I write this down with the double bonds and the triple bonds, I think of this passage in Ecclesiastes that I wanted to read to you. Because, weakest, we get stronger. This is the strongest one here. And it says in Ecclesiastes 4:9, it says, 2 are better than 1, because they have a good reward for their labor. For if they fall, one will lift up his companion, but woe to him who is alone when he falls. Who can tell me, when Jesus sent out his disciples to preach in the different cities, he sent out 70 at one point. Did he send them out to 70 different places all alone? That's not how he did it. How did he do it? He always sent them out 2 by 2, right? He always sent them out 2 at a time. Paul, in his missionary work, we never really think of Paul all by himself. We think of Paul and Barnabas, or we think of Paul and Silas. Sometimes it was Paul, Silas, and Timothy, but it was always a group of them that were going together. So this kind of highlights that. The Lord, he didn't send them out all by themselves. He sent them out 2 at a time. That's better from an accountability perspective. It's better for encouragement. It's better, like it says, if one falls and the other one's able to lift him up, if you've got 2 of them. Again, if 2 lie down together, they will keep warm, but how can one be warm? You see these animals when it's cold, you know how they get huddled together? Dogs will do that and sleep together to help stay warm. Though one may be overpowered by another, 2 can withstand him, and a threefold cord is not quickly or easily broken. And so I always think about that passage, and to me it's sort of appropriate. When I think of that threefold cord, I think about some relationship that we're involved in, maybe like in marriage, right? A husband and a wife being bound together, or having a close friend, a couple of you being bound together. Well, the strongest that relationship's going to be is when it's a threefold cord. And that is when Christ is that which connects you guys together, right? I'm counseling someone that's getting married now, and I told him, I said, most marriages today, sadly, they fail. They don't make it, right? And if we try to build a marriage on a foundation other than Jesus Christ, we're kind of setting ourselves up for failure. But when we have that threefold bond of Christ being there in the center of it, we've got the strongest bond that's going to hold that together. Same thing with close friends. You got a friend that loves the Lord, you love the Lord, you're going to be the best thing for one another. That's a friendship that's going to last and that's going to be able to help you. So anyway, just something that I always think about when I think about the double and the triple bonds. Every time I write those down, I think about that threefold cord. So let's do an example. Page 133, example 5.2. An example that has a double bond in it, and that is the Lewis structure for, what's the compound? C what?
CH2O.
CH2O. All right. CH2O. CH2O. So let's write down C. We know is in column 4A, 4 dots. H, 2 of those, each with a single dot. And then O has 6 dots in column 6A. We'll just write it like that. All right, so again, which atom needs the most electrons to be ideal of these 3?
C.
C does, right? So we want to put C in the middle. All right, whichever one needs the most electrons, start by making that the central atom, the one that's in the middle of your structure, okay? That's usually how it works out. So, this one's kind of obvious. We take this H, we rotate it up here. These guys are shared. We could take this H, we could plug it in right here, right? These guys are shared. So carbon's got 2 more electrons to offer. Oxygen needs 2 to be ideal, right? So it should be sort of obvious to us that these guys could be shared here, and then this guy. Whoa, that's not going to work. Let's share this guy this way. There we go, and then we'll share this guy this way. There. Trying to figure out what I see in that. There's some kind of like sea serpent in here. You kind of see that going on? Maybe no. This is actually a snake on the ground. It's trying to eat an egg. You got it? You guys see it? All right. So we've got a bond between. If we look at this, our shared electrons, we've got a bond between the C and the H right here. We've got a bond between another C and H here, and then between the C and the O, we've got a double bond. 2 pairs of shared electrons, right? And so the only other thing we need to do at this point is we need to make sure we put in any dots that for the unshared electrons. So we could go back and look at our original one. I mean, if we look at kind of what we did here, there we can see that they're hanging out here off the oxygen, right? But then we can count it up to make sure we got it right. So here we got 2, 4, 6, 8 around the oxygen, 2, 4, 6, 8 around the carbon, and then for each hydrogen we got 2, which is what hydrogen needs to be ideal. So we count them up, we're good. This is kind of wacky. So maybe what you would want to do actually on your paper that might be easier for you to see is kind of put a hydrogen up here with its single electron, and a hydrogen over here with its single electron, and then you could put your oxygen over here. You could draw your Lewis structure that way as well, and then anytime you've got electrons between 2 atoms, then just replace that with a line for each pair of electrons, right? You could do it like that as well. However, it's easiest for you to see that they're sharing these, and just make sure you replace the shared electrons with a line. Any other questions about that problem? Let's do one more, HCN, which is an example of a compound with a triple bond. So HCN, H has a single electron, C has 4, like that. N, how many does N have? Which column is it in? 5, right? I kind of expected that because look right here. Here's a shared pair of electrons. Carbon has 3 more to offer. So I'm expecting if there's only one more element, it's probably an element that needs 3 electrons to be ideal, right? So we write down 5 for that. So these are shared, these are shared, these are shared. So 3 shared pairs of electrons between the carbon and the nitrogen, only 1 shared pair between the hydrogen and the carbon, so it's going to look like this, with a couple of unshared pairs hanging out there off of the nitrogen. We count them up. 2 here, 4, 6, 8 on the nitrogen, 2, 4, 6, 8 for the carbon, and 2 for the hydrogen. So everybody's ideal. All right, no questions about that. I'm going to move on to naming covalent compounds. So any questions about either of those examples? Man, you guys are so smart. I don't even know why I'm here. All right, can I just stay home?
No.
And still get paid?
No.
All right. So let's go on to naming covalent compounds. So let's think about ionic compounds for a minute, just so that we can remember the differences between how you name ionic compounds versus covalent compounds. Ionic compound, NaCl. What's the name of that compound? Yes? Sodium chloride, says Isabella. Does everybody agree with her? Yeah, that's right. She's right. Sodium chloride. So the only rule that we have to remember if it's an ionic compound, and how do we know if it's an ionic compound? What's our quick way to figure it out?
It's a metal.
Does it have a metal in it, right? If one of the atoms in here is a metal, if one is a metal, then it has to be an ionic compound. Na is in one of the first 2 columns. It's the proper color. What is it, green, or what's the metals? Purple. Last book we had, I think, was green. So it's a metal, so we know this is an ionic compound. So the naming convention is that for the metal, you just use whatever the name is of the metal, and for the non-metal, we just put an "ide" on the end of it, right? And that's the naming convention. It doesn't matter, even though it would never have this, but if it was Na2Cl or if it was NaCl3, right? It wouldn't matter. We would call it sodium chloride. Don't let that confuse you, because that can't happen, right, the way these ionic compounds combine. But my point is, it doesn't matter how many of the atoms you have, it would still just be whatever the name of the metal is, and then the name of the non-metal, but with "ide" on the end. That's our simple way to name those compounds. Covalent compounds are a little trickier. With covalent compounds, we have to know some prefixes. And you're actually already used to doing this. You probably just don't remember or haven't thought about it much, but probably most of you know what each of those compounds are. What's the first one? Carbon monoxide. Wait a minute. You do it back. Wait, is it like that?
Yeah.
Okay. Yeah. I tried to do IE the first time. That's right. I knew it was the opposite of what I initially thought. All right. So carbon monoxide. What's this one? Carbon dioxide. All right, now I can see you like shot your hand up. You were ready to say it, but they kind of stole your thunder, so I'm going to give it to you anyway. All right. So the key here is these prefixes. Mono meaning one, di meaning two. It's just like in homonuclear diatomic, right? It's a diatomic. It's two atoms that are joined together. So we need to know the prefixes when we're working with covalent compounds. And you need to memorize 6 prefixes for this class. All right, so memorize that mono equals 1, di equals 2, tri equals 3, tetra equals 4, penta equals 6, and then penta equals 5. I got to count momentarily. And then hexa equals 6. Make sure that you know those prefixes. And then use them this way to name covalent compounds. Follow these rules. 1, put prefix in front of first element unless there's only one atom. So in the case of carbon monoxide and carbon dioxide, the reason we didn't call that monocarbon monoxide is because if it's the first element and there's only one of them, you don't use the prefix. If there had been 2, if it had been this, we would have called that dicarbon monoxide. So if there's more than one of the first element, you use the prefix. If there's only one of the first element, you don't use the prefix. Does that make sense? You kind of, your mouth hit the floor whenever I said that. Yeah? It just blew her mind. Now, are you clear?
Yeah.
Does that make sense? Okay. All right. For the second element, you always use the prefix no matter what. Okay? So always put prefix in front of second. And then you also do the same thing that we did with the ionic compounds. In the second element with ID. So we'll do a couple of examples to let you guys practice that. First example, they give us, let's see, I'll let you finish writing. I want to swallow. cherry coke anyway. Yes. Yeah, go for it. So this is example 5.3 on page 135. And they ask us, what is the name of P2O5? Question for you, do I need to look at the periodic table for anything? No? No? Oh, wait a minute. There was a no and there was like, wait, why would I need to look at the periodic table?
No, there's no reason.
Huh?
There's no reason.
There's no reason. So if I said give me the name of NaCl, and then I said give me the name of P2O5.
Well, you might need to in case it's a metalloid.
You need to figure out first, am I dealing with an ionic or a covalent compound? And the way that I do that is I look to see, is there a metal in this compound, right? So we do need to check out the periodic table just to verify whether or not there's a metal in the compound. So this one, Na is a metal, so that's an ionic compound and follows the naming conventions of the ionic compounds. This one, however, P and O are both nonmetals, right? P is in which column? The fifth column, yep, 5A, it's blue, it's a nonmetal. So this is clearly a covalent compound, right? No metals in it. So I'm following these naming conventions, right? So the first one, put prefix in front of the first element unless there's only one atom. There's more than one atom, there are two. So what would the naming convention be for the first element in this compound? Diphosphorus, exactly. Di, we have to use the prefix because there's more than one. Diphosphorus. And then for the second element, we always use the prefix. So there are 5 of the second element. So we know the second element's going to begin with penta, right? Penta. The second element is oxygen. But our third rule says on the end of it, you got to put "ide," right? So it wouldn't be pentaoxygen, it would be pentaoxide. So the full name of our compound would be diphosphorus pentaoxide. Make sense? Simple enough? A little bit more complicated than the ionic compounds, but still not hard, right?
And if that was PO5, it would just be phosphorus.
That's right. Yep. Her question was, what if they had given us this? You would just remove it. There would be no prefix on the first one.
So when do we use mono? If it's on the second
Only
one?
on the second one. Yep. Yep. You'll never have mono on the first one. Only on the second one. Okay. And then now they reverse it and say, this time give me the formula if the name of the element is sulfur trioxide. All right? Sulfur trioxide. Now, tell me this. For this element, do I have to look at writing this compound down, do I need the periodic table for anything? Cruz says no. Why?
Because you already know the number as well as the two elements.
I already know the number as
You
well as
already
the
know
two.
if it's a metal or not because it has tri at the beginning.
You know that
Or it's a
it's a
non-metal.
covalent compound because it uses the prefix, right? As soon as you see a prefix in there, you know you're not dealing with an ionic compound because we never use prefixes in ionic compounds, right? So as long as I know what the chemical symbol is for sulfur and oxygen, I don't really need to use the periodic table for this. So it's just going to be S. There's only one of those because there's no di or tri or anything in front of it, and there's a tri in front of the oxygen here, so it's going to be 3 oxygens. So it would be that. Yep. Yep. All right, questions about any of that, about the naming conventions? Okay, cool. Let's one more thing, and then I'll let you go. Let's talk about. Oh, what time is it?
220.
2:20. Okay, we're good. We're in much better shape than we were the last class. Let's talk about electronegativity and polar covalent compounds. What are polar covalent compounds? We're going to find out. Electronegativity. Electronegativity. You know what? Actually, I'll title this session Electronegativity and Polar Covalent Compounds. Right. I think that's what he entitled this section in the book. But before we dig into what those are, let's talk about atomic radius. So as it turns out, in covalent compounds, how are the bonds formed? What's a covalent bond by definition, did we say? It tells us that the electrons are what? They're shared, right? The way that this compound is held together is because it's a physical bond where the electrons are shared between the elements in the compound, okay? But as it turns out, the electrons that are being shared are not always equally shared between the atoms in the compound, okay? So sometimes certain atoms are going to pull harder on the electrons and be it's kind of like, you know, you say you're going to share the Snicker bar with me and you cut it what you call in half, right? And I get like a little snack-sized bite and you've got this huge piece of Snicker bar out there. It's just not right, you know? Well, that's the way some of these atoms are. They just don't share evenly, right? And so, yeah, it's an example of unfairness, right? But so let's talk about atomic radius because that has some bearing on the way these electrons are shared. And the atomic radius is the distance from the center of the nucleus to an atom's valence electrons. And I mean, this should make sense to us, you know, based on what we know about the term radius in math, right? When we talk about a circle and we have a point in the middle, the radius is the distance from here to here, right? And so when we talk about atomic radius, think of the point in the middle as the nucleus, right? Because that's what's at the center of the atom, and all of these electrons are orbiting around that nucleus. Well, the valence electrons are the electrons that are out in the furthest orbits, right? So that's kind of like the full size of the atom. And so the distance from whatever that furthest electron is out there to the center of the atom where the nucleus is, that's what we call the atomic radius, right? The radius of the atom. So that should make sense to us. Well, as it turns out, as you go down the rows of the periodic table in a given column, it should make sense to us that the atomic radius is going to get bigger. Because what do we know happens as we go down to those different energy levels, right? Each row corresponds, I kind of gave the answer away. Each row corresponds to an energy level, and so as we travel down the periodic table, the energy level, the radius is getting bigger. It should make sense that it's getting bigger because, right, for hydrogen and helium, or for helium it's just 1s2, right? You go down to the next energy level and you got 1s2 and you got a 2s2, and you also got a 2p6 if you go all the way across that row there. And so each time, what's happening here is this atom is getting bigger. And so the atomic radius is increasing. Does that make sense? As you go down in a particular column, that the atomic radius would be increasing because more electrons are being added, and so the atom overall is getting bigger. And so what I want us to realize that based on that, so the other thing that happens is, well, let me just say this. So as travel up the periodic table, I'm gonna leave a space here. As travel up and blank on periodic table. So as travel up on the periodic table, the atomic radius decreases. That's just the reverse of what we said a minute ago. As you travel down, the atomic radius gets bigger, right? As you travel up in a single column on the periodic table, the atomic radius decreases. So as you travel up, and what if you're instead of in a column going up and down, what if you're in a row going left to right? Which direction do you think the atomic radius would decrease in? If I'm going, You think going to the left, the atomic radius would decrease?
I think to the right it would increase.
You think it would increase to the right, the atomic radius would?
And to the left it would decrease.
That's kind of what I would think too, but that's actually not true. I mean, when I was working it out in my mind, until I saw a Y, and then I was like, oh, okay, that makes sense. Here's the reason why. What happens, so we haven't increased in energy level, right, as you go right and left. We're staying in the same energy level. But what does happen as I go further to the right, let's say we're on row 2 here, right? Let's say we're just on, let's say we're on boron, right? Boron has an electron configuration that looks like that. Okay? Now what if you travel more to the right in this row here? Let's say you go from boron all the way to neon, okay? So boron looks like that, but neon looks like this. So it's got the same orbits here, but the only difference is it's got more electrons in that outer orbit, right? So what happens is as the number of electrons increase in that outer orbit, remember what's in the middle of the nucleus, you've got positively charged particles. So as you've got more positively charged particles and more negatively charged particles out here, the attraction between those two becomes stronger. And so what it does is it makes the radius actually decrease as you go to the right. All right? So if you're on the same row, as you travel to the up and to the right, on the periodic table, the atomic radius decreases. All right? So to the right and up, atomic radius decreases. Why did we talk about atomic radius? Because we want to make a comment about electronegativity. Electronegativity is a measure of how strongly atoms attract electrons in a covalent bond. It's what I was talking about a minute ago, how some atoms attract have a hold on the electrons more than other atoms do. They're not sharing electrons fairly. And so electronegativity is a measure of that, how strongly an atom's attraction for electrons are in a covalent bond. All right? And so as it turns out, for En, for electronegativity, as travel up and to the right, on the periodic table, electronegativity increases. All right, so same as we were looking at before, but electronegativity increases while atomic radius decreases. Because as the radius decreases, as those outer electrons get closer to the nucleus, the pull on those electrons is stronger, right? And so that's why if atomic radius decreases, if the atom becomes more compact, then it's going to have a stronger pull on any electrons that are shared. So that's why these kind of flip-flop. Atomic radius decreases, electronegativity is going to increase. So just, if it's easier for you, instead of kind of reasoning through that the way that I explained it to you, just remember up and to the right on the periodic table. Smaller radius, greater electronegativity. All right? And the reason why we needed to define that is because we wanted to understand the definition of what we refer to as a polar covalent bond. And so that's the last definition I'll give you, a polar covalent bond. In a polar covalent bond, this is a covalent bond in which the electrons, the E's, are not shared equally. So, if we have a compound like HCl, which is the example that they used in the book, if you have a compound such as HCl, H is at the very tip top of the periodic table. But it's on the far left, right? Cl is also near the top of the periodic table, but it's almost all the way to the right, right? It's in the next to the last column. And so because of that, because both are kind of near the top, but Cl is far to the right, then it's going to have a stronger electronegativity than hydrogen does. And so the Cl is going to be unfair, and it's going to get the bigger piece of Snicker bar, right? It's so wrong. It's not. See, you're just like my wife. You're laughing about it. You think that's funny that I got the smaller end of the Snicker bar. All right. So this guy is actually it's being pulled over there. The electrons being pulled stronger. The shared electrons being pulled stronger by the Cl. So it's shared unfairly. Now, when we talked about Cl. Right, so I mean, remember with HCl, this is what its Lewis structure would look like, right? With one shared electron pair, but like I said, it's actually pulling it over there, so it's stronger that way. But we also looked at Cl. In a covalent bond with another Cl atom, and it looked like this. Well, in this case, it's exactly the same element, right? And so they're pulling on it equally. And so this is not a polar covalent bond. This one is nonpolar because one's not pulling stronger than the other. But in the case of HCl, the Cl has higher electronegativity, so it's pulling unfairly on the electron, and so it becomes a polar covalent bond. And so we're going to get more down into the details of that in a couple of weeks when we get back. But I just wanted you to understand this concept of electronegativity and be able to look at the periodic table and say, oh, because of where this is located, it's going to have a greater electronegativity than this element over here. Okay? Any questions? All right. You guys have a good one.